I were to perturb the system by adding a little bit of energy, by changing the parameters a little bit, then this formula tells you how the entropy will change under that small perturbation. One of the ways of bringing out the point that I'm not doing this in a remotely historical way is you'll notice I've done the second and first law in reverse order. Okay, and then an awful lot of the content of thermodynamics only comes up when we allow multiple systems to interact with each other, multiple systems that are individually thermodynamic systems. And in particular, here's how that goes. I can put systems in thermal contact, which is to say that energy can flow between them, but the other conserved quantities remain separately conserved. And there are generalizations of that where I might allow values of some of the conserved quantities to flow between the systems. So if you imagine I take a box of gas where there's a barrier in between that separates one chunk of gas from another chunk of gas, and if I then allow the barrier to move freely, that's a system that allows the volume parameter of each box to change while keeping the total volume fixed. If I allow particles, if I've got two gases, I allow particles to flow between them, the total number of particles stays fixed, but I'm now allowing a change of particle number for each box separately. But the main one relevant to us here is thermal contact, where all the parameters other than the energy stay fixed, but I'm allowed to have energy transfer between systems. And we then assume, crucially, that thermodynamics doesn't just apply to those individual systems, it applies to the combined system, so that I can treat that whole system as one thermodynamic system. And that means it has a single unique equilibrium state, which is going to be characterized by the total conserved quantities, including energy, of the two systems together. And that means, generically, when I put two systems in thermal contact, they will equilibrate. And we assume that the second law, the rule of the non-decreasive entropy, generalizes to require that the total entropy, the sum of the separate entropies, is non-decreasing in any adiabatic process. Instead, if you were watching carefully, you'll see that my original statement of entropy only fixed entropy up to some arbitrary positive scaling. If the only thing that characterizes entropy is not allowed to go down, then you can replace entropy with any increasing function of entropy and you won't affect the root. Locking entropy down, fixing it up to an overall scale factor and an additive constant per system is required by taking the total entropy of a system to be the sum of the entropies of the subsystems. And from that follows, in ways I won't review here, a lot of the sort of mechanical content of thermodynamics. We get out the idea that the best way in which, the best you can do in terms of trying to get usable energy out of a thermodynamic system is given by running a Carnot cycle between them. We get out the maximum efficiency, if any process that does that, and particularly we get out the Clausius and Kelvin statement of the second law. We get out the fact that there's no intervention I can do in a system whose only effect is to transform heat into work. There's no intervention I can do whose only effect is to cause a net heat flow from the cooler to the hotter of two systems. Okay, so that's thermodynamics. That's my sort of target point. Let me add one other part of it. I think this last part isn't part of thermodynamics proper, but it's part of a lot of the application of thermodynamics, particularly in astrophysical contexts. And that's what gets called the idea of local thermal equilibrium. So if I've got an extended body like this table or like the air in this room or something, very often it's possible to treat small chunks of the body as at equilibrium individually, even though there's heat flow, particle number flow from one region to another. And roughly speaking, the criterion is that the processes in that region which equilibrate it are fast compared to the processes that move energy or other locally conserved quantities between that system and other systems. And that lets you write down a story involving transport equations that let me characterize an extended body, not just by its overall thermodynamic properties, which don't apply, it's not at equilibrium, but by thermodynamic functions that tell me the temperature as a function of position in the body, the pressure as a function of the position in the body. I give you transport equations that tell me how energy and other quantities flow through that system. So, for instance, the Navier-Stokes equation tells me about fluid flow. Ohm's law tells me about how current flows through conductors and how it dissipates and generates heat. And none of this is derivable from basic thermodynamics, but all of it takes the basic thermodynamics as a starting point. Okay, so much for thermodynamics in general. Let me say just a little bit about how gravity tangles up the story even before we get black holes in the picture. And there's a lot of literature, and some of it's quite contested, about just how to think about thermodynamics and statistical mechanics in self-gravitating systems. rather than try to give a general story of this kind, I actually want to discuss a particular model due to Sorkin, Wilde, and Ginn from about 30 years ago, which sort of illustrates a lot of the features that are going to be of interest here. So Sorkin and Wilde Ginn's model, it's just a sphere. The sphere is full of radiation. It's completely characterized at equilibrium by the total mass of the sphere and by the radius of the sphere. So you can imagine the walls of the sphere being perfectly reflecting, having negligible mass, the radiation is sitting in the box, and it's at thermal equilibrium. So if the box is, about to say really big, that's slightly misleading. If the ratio between the mass and radius of the box is such that the radius of the box is smaller than the Schwarzschild radius of that much mass, then of course the thing is a black hole, and we can't think about it as a sphere of radiation from the point of view of anyone outside. An event horizon would form around it, and we wouldn't be able to see any of its physical details. So we're only really interested in the regime where the Schwarzschild radius of the mass in the box is smaller than the actual radius of the box. Now, if the Schwarzschild radius of the box is way, way smaller than the actual radius of the box, that's a good proxy for saying gravity is not super important in the physics of this box. And in that circumstance, this just behaves like an ordinary radiation gas. I'm sure real radiation gases are self-gravitating, it's just we can normally neglect it. And then it behaves itself perfectly happily. It has an extensive set of thermodynamics, the entropy is proportional to the volume of the gas, and everything's quite well behaved. So we're interested in what you might call the strong gravity regime, where the box is bigger than its Schwarzschild radius, but not way bigger than its Schwarzschild radius. You get interesting physics when the box is about sort of 5 times its Schwarzschild radius. And here's some interesting features of a thermodynamic system like this in that regime. First observation, if you want to say what do we mean by the mass of the box, we can no longer say what we mean is the sort of integral of the mass density of the box over all of the box. Because in general relativity with curved space-time, what I mean by the mass is something like the appropriate mass density is something like the appropriate component of the stress energy tensor. In a curved space-time, if I've got a tensor here and a tensor here, there's no well-defined rule to add them up to get a total. So what do we mean by the mass of the system? We define it asymptotically. We go out to a very large distance from the box. We say that far from the box, space-time is virtually Minkowski. Therefore, I can just appeal to ordinary translation invariance and a time translation asymptotically. I can appeal to Nernst's theorem, and I can get out an asymptotically defined mass. The slightly more careful version of that gets called the ADM mass, but the basic shape of it is just that sort of Nernst's theorem argument. Second observation, the whole system's at equilibrium, so the temperature is just the total property of the system. But if you ask what's the locally measured temperature look like, it goes up as you go deeper into the box. So imagine just entering the box carrying a thermometer, and then the thermometer will get hotter as you go closer to the middle of the box. A way of thinking about this is there's time dilation as you go closer in, and so the temperature is related to the energy is defined by the asymptotic time coordinate, the local time coordinate is now deviated from the asymptotic time coordinate, and so you get effectively a blue shifting of the temperature as you go deeper into the sphere. Third observation, this system is highly non-extensive, highly non-homogeneous, so the density of radiation is not remotely constant across the box. There's no meaningful way in which you can say that having the box twice as big will just lead you to the same thermodynamics, locally speaking. In fact, if you make the box twice as big, generically you're likely to cause it just to collapse and get highly unstable. And it has a negative heat capacity, which is a general feature of strongly gravitating systems. If I were to allow heat to flow out of the box, its temperature would go up. And so that means that it's unstable if you were to put it in a heat bath. And it means that if I want to talk about thermal contact between two systems, which recall as one of the big components in thermodynamics, I need to do it carefully. I can't just take the two spheres and put them in physical contact with each other. Gravity is a long-range force. The gravitational effect of one sphere on the other will cause big effects in the thermodynamic state of one sphere due to the gravitational effects of the other sphere. So if I want to allow heat transfer between one system and another, I need to use an intermediary of some kind. The simplest way is something like I can take a little box, I can lower it into the first sphere, I can let it fill up with radiation, I can pull it out again, I can take it away to the second sphere, which is way over there, and I can lower it in and I can allow the radiation to flow out. there are other ways of doing it, but in general, you're going to have to do tricks of that kind. You can't physically locate the boxes close to one another, because then they're not just in thermal contact, their gravitational effects are going to distort one another.
I'm really sorry about this.
Oh, sorry, I thought you meant about black hole thermodynamics. I was going to say, you may be sorry about it, but that's what's in Sorkin and Al's paper, and you have to realize.
I hope they won't do anything too loud. It's rather unpredictable. I think you missed the guy who was actually walking outside the windows. Like, people are so keen to get in here to hear your talk.
Yeah, exactly. Unimpressed by how elitist your framework is. Okay, so much for thermodynamics in general. So with that as a starting point, I now want to look at black holes in particular and see the extent to which black holes are realizers of this basic thermodynamic description. And initially I want to consider the story in classical physics, by which I mean physics where we can treat all of our systems phenomenologically as classical systems. So for instance, just to clarify what I mean by classical here, I'm including something like a radiation fluid as a classical system. Why do I say that? Because I can just write down an equation of state for radiation fluid. I can treat that equation of state in classical general relativity. I'm not considering superpositions of it or anything like that. Nonetheless, it's not the case that I could derive the radiation fluid equation of state from classical electromagnetism via classical routes. You need the quantum theory of radiation to get out the thermodynamics of radiation. But I'm just treating that as a black box at the moment. What I mean by classical is that I'm not going to consider quantum field theoretic effects. I'm not going to consider the arguments that take us to the Hawking effect, which that's the second half, if you like. Okay, so there's a starting point about even trying to think of black holes as thermodynamic systems which needs to be addressed. So in general relativity, the standard definition of a black hole is that it's a region of, loosely, it's a region of space-time such that light can't get from that region to future infinity. So at that point, there's actually almost like a category error in supposing that a black hole defined that way should be a thermodynamic object. Thermodynamic objects are objects. They persist through time. They have time trajectories. They are three-dimensional things. Their thermodynamic properties are a function of time. The black hole defined in general relativity is a space-time region. It just is. And so, for instance, talking about there being, let's say, two black holes merging in that description, or one black hole moving towards another is just very hard to make sense of. In fact, even saying what we mean by there used to be two black holes, now there's one black hole because they've merged, is really difficult under that definition. But the relativist definition of a black hole, the relativist conception of a black hole isn't the only one in play. Even before we start worrying about thermodynamics, then astrophysicists have been talking about black holes as if they were objects, for decades and decades, and it plays a pretty important role. So when one says, for instance, that in the centre of the Milky Way there is a supermassive black hole, when we say that in the centre of other galaxies sometimes there are binary black holes, when we say that LIGO has detected several collisions of black holes in the last year, then we do again seem to be talking about something that's a bad fit to the general relativity definition of black hole. And to sort of address those conceptual problems in the mid-80s, don't forget my comment about very much assessing things from where we are now rather than at the dawn of black hole thermodynamics, Kip Thorne and co-workers developed what they call the membrane paradigm to sort of work around that conceptual problem. And the way the membrane paradigm works is something like this. You take a surface, spherical for a non-rotating black hole, and you put it just outside the event horizon of the black hole. Now the event horizon, sorry, when I say just outside, Thorne et al. Said maybe 1% further out than the black hole, but in modern quantum gravity uses, the general tendency is to put it so close to the black hole that it's like one proper Planck length distance from the black hole event horizon, so that the area of this stretched horizon is only one Planck area larger than the true horizon. So if you think about the definition of the true event horizon, nothing that crosses the event horizon can get back again. But nothing that crosses the stretched horizon can get back again unless it accelerates so hard as to be requiring quantum gravity levels of energy. So if you've got sub-Planckian energy available in your acceleration, the stretched horizon is a point of no return just as much as the true horizon is. But the nice thing about the stretched horizon is it's time-like. So there's time dilation of the surface of the stretched horizon is enormous, but it's not infinite. So I could think about the stretched horizon as an object that persists through time, and I can consider how that object moves with respect to other objects, how many of those objects there are at a time, and so forth. So what we're going to be looking at in the way I'm going to construe black hole thermodynamics, we want to say to what extent can we think of the stretched horizon as a thermodynamic object with thermodynamic properties. That's the setup for what we want to try doing. Okay, so let's go through some of those properties of thermodynamic systems that we discussed earlier. So starting with the idea of equilibrium and equilibration. It's been established fairly thoroughly by the standards of rigor of modern theoretical physics, you might say, via what get called no-hair theorems, that for a given mass and a given charge and a given angular momentum, and on the assumption that I've got stationarity, so no evolution in time, that the Kerr-Newman family of solutions are unique. So a Kerr-Newman black hole is a stationary, rotating, charged black hole. No-hair theorems tell us these seem to be the unique stationary, charged, rotating black holes. There are loopholes and issues to be concerned about, particularly in dimensions larger than form, with exotic forces in play. But let's put it this way: I think we're at least as solid at this point about the uniqueness of equilibrium of black holes as we are about the uniqueness of equilibrium of ordinary thermodynamic systems, like boxes of gas and hot iron bars and the like. And I think it's an important comparison point to hold on to. The relevant point here isn't have we established black hole thermodynamics with full mathematical rigor, it's have we established black hole thermodynamics to the same level of confidence that we have for ordinary thermodynamics. What about equilibration? Well,
Sorry, just really quickly, when you say level of confidence, do you mean empirical?
No.
Okay, good.
As a mathematical claim.
Yeah, as a right.
Yeah.
Okay.
Yeah. As a mathematical claim inside classical GR.
Yeah.
So if we look at how quickly systems, non-stationary black holes approach stationarity, and in particular we look at perturbations of stationary black holes, we have a bunch of numerical and analytical evidence that they equilibrate pretty fast, so that if you perturb them away from equilibrium, they return to equilibrium. So for instance, we know how to think about the vibrational modes of black holes. We know those vibrational modes are heavily damped, so we know if you perturb a black hole so that it's vibrating, then those vibrations damp down, and we know the time scale on which they damp down. And I couldn't have said this if we were giving this talk even 2 years ago, but since LIGO came on stream, we have observational confirmation of those damping down processes. So more or less uniquely in the talk, for this particular bit, I actually mean empirical. And the fit, if you've seen some of the graphs here, the fit between the theoretical predictions of black hole ring down after merger and the LIGO measurements of it is startlingly good. Okay, so equilibrium and equilibration looks pretty good to me. What about irreversibility? So for ordinary systems, we have these sort of infinitesimal adiabatic transformations I can do that let me move the system around the space of equilibrium states, provided I don't increase the entropy. Now for a black hole, there's a bunch of small interventions I can do that let me move around the space of stationary black holes, provided I don't decrease the surface area. So for instance, say I take a charge and I lower the charge into the black hole. That will increase the charge of the black hole. Assuming it's the same charge as the black hole, it'll increase the charge of the black hole, it'll increase the mass of the black hole. If I lower it slower and slower, then I'll get less and less mass increase, but what you find is that even in the limit as you lower the charge infinitesimally slowly, the total area of the black hole can never go down. Go up as much as you like. If I throw mass into the black hole on a trajectory that just brushes the horizon, I can increase the charge of the black hole and the mass of the black hole in such a way that holds the total area of the black hole fixed. If I throw it in on a trajectory that's a bit more normal to the surface, then the area will increase. If I was trying to throw it in so as to decrease the surface area, I can't do it. If I were to use the Penrose process, so I fall towards the black hole and at point of closest approach I throw my poor graduate student out the back, and they fall into the black hole.
Thanks, dude.
Sorry, too sharp. Then I decrease the angular momentum and I get some energy out, and in doing so I increase the area of the black hole. In the limit, as my trajectory comes closer and closer to the black hole, the increase in the area of the black hole gets smaller and smaller and smaller, but it can never be negative. So, claim if we look at the sort of adiabatic transformations of black hole, then they have exactly the reversible, irreversible, forbidden structure that we saw in standard thermodynamics, with the area playing the role of the state function that tracks which processes are permissible. And Hawking's celebrated area theorem generalizes that from infinitesimal processes to arbitrary interventions in the black hole. Under certain assumptions about the global structure of space-time, we can establish that no intervention on a black hole can decrease its area. I mean, that's not simply a generalization of the infinitesimal results, which are due to sort of Christodoulou and Ruffini in the early 70s, because of course the Hawking's result doesn't tell us that any transformation that doesn't increase the area can be performed. And as I was stressing in the thermodynamic case, that's actually quite an important component of the ordinary story about thermodynamics, that it's not just that I can't do the processes that decrease entropy, I basically can do all the others. Okay, what about the first law? Well, if I've got a black hole of mass m and charge q and angular momentum j, then I can derive this formula just as a matter of, the j in the, where are we? The second j should be a q, I'm sorry. So this relates infinitesimal changes in mass, area, charge, and angular momentum. Observe it has the same functional form as the first law of thermodynamics. In ordinary thermodynamics, slightly more than that actually. So if I had the ordinary thermodynamics of a body whose equilibrium was characterized by charge, angular momentum, and mass, the thermodynamic parameter conjugate to charge has to be the electric potential. The thermodynamic parameter conjugate to angular momentum has to be the angular velocity. So it's not just has the same formal structure, with the possible exception of the surface gravity in the area, the physical interpretation of these quantities is the same in both cases. So if I interpret temperature as proportional to surface area, if I continue to interpret entropy as proportional, temperature is proportional to surface gravity, if I continue to interpret entropy as proportional to area, then that has exactly the thermodynamic functional form. It doesn't fix the overall scale of the entropy temperature. And that expression can be thought about, can be derived in two different ways. I can think about it as an equilibrium state condition of how I move around mathematically the space of equilibrium states, or I could think about it in terms of physical processes of what happens if I perturb the black hole by chucking in small amounts of mass or charge, and I get out the equilibrium state and physical process interpretations that way, and I get out numerically the same mathematical expression. So there's a consistency check, if you like. The physical process of equilibrium state interpretations of this both go through. Okay, so far so good. And let me digress in the order slightly. Oh, I should say, yeah, perhaps it's worth stressing here that most of the discussion here, well, all the discussion I've had so far here has taken classical general relativity as a starting point with the Einstein-Hilbert action. If I generalize general relativity, I can imagine doing that by adding arbitrary diffeomorphism covariant terms to the action of the theory. In particle physics, we generally think that the Einstein-Hilbert action is only the sort of leading order term in an infinite expression for all the various quantum corrections to general relativity. And so it's interesting to ask what happens if we don't just consider general relativity, we consider an arbitrary diffeomorphism covariant theory of gravity. And Wallace shows that you can derive a version of the first law for exactly that process. So A is no longer the area. It's a pretty complicated expression whose leading order term is the area, but includes higher order corrections from other terms in the GR dynamics. But you still get out exactly this expression. It still has the physical process and equilibrium state interpretations. And you can show, at least for infinitesimal interventions of the black hole, that this new concept of entropy also continues to play the role of a tracker of permissible processes. So far as I know, there isn't a result of the sheer generality of Hawking's result for this generalised notion of entropy, but you can do it at least for the infinitesimal interventions. Okay, let me digress a little from the order here, and yeah.
So you're saying that if you put a little bit of, let's say you have a gas in the box, so it has some entropy associated with it. You lower it in the black hole, then you can show that the increase of the area of black hole will make up for the loss of entropy. Is that?
No, definitely not. I haven't said that. That would be a situation where you've got two thermodynamic systems.
Yeah.
So far, everything I've said has been about a single thermodynamic system where I'm intervening with it without putting other systems in thermal contact. And that's important.
Can I ask a quick question?
Yeah.
So when you talk about physical processes moving you from one equilibrium state to another, in a setup, does that abstract away from the question of dynamical stability of the current solution? It's an open question.
Yeah, I don't know anything rigorous out there. I mean, being casual about it, those transformations are going to perturb the black hole slightly away from equilibrium. If you hand over to the sort of general evidence we have mathematically that if the perturbations away from Kerr-Newman equilibrium get damped back down to Kerr-Newman, then we have good reasons falling short of a theorem to think that you get back to where you started doing it. In terms of what's going into the derivation, I think it's just assumed in the form of that derivation that the system will settle back down to Kerr-Newman state, but I'm not certain of that.
Right, because I think this is an open question, whether even small perturbations will lead to blow up very quickly.
So it's sort of a methodology question. For me, it's not really an open question because I think the evidence is pretty overwhelming. For a mathematician, it's an open question because there's no theorem. But there's a lot of analytical and numerical modelling that seems to support it pretty strong. But yeah, I mean, clearly it'd be nice to have a theorem. Okay, so before I talk about thermal contact with multiple systems, which is the point just raised, which will complicate the story a lot, let me just briefly talk about local thermodynamics from the point of view of black holes. And this to me was one of the most striking things when I was looking into this. So even though this membrane we put at the surface was, in a sense, completely fictional, we can actually treat it as a physical extended body with thermodynamic properties. Specifically, we can treat that membrane as a conducting viscous fluid. And within classical GR, we can derive a whole lot of results within that story. So for instance, say I drop a charge onto the black hole. Here's how that's described in the membrane paradigm. The black hole is initially uncharged, but we treat the membrane as a conductor. So as the charge falls towards it, it pulls, so say it's positively charged, it pulls negative charge through the membrane towards the point of the black hole close to approach. So the black hole is now unevenly charged with negative charge on the side approaching the falling charge, positive charge on the far side. Because of that current flow, because the black hole has a resistivity, 733 ohms, I think, in SI units, then that current flow dissipates energy as heat, which increases the surface area of the black hole. When the charge arrives, it then spreads out as further energy dissipation through Ohm's law, and at the end of the process, the whole thing has settled down again with the charge distribution uniform, and I'm back to stationarity. And you can calculate in that story how much energy should be dissipated, and you can check that against calculations that are just done without that story at all, and you can derive the general form of that and see that it precisely reproduces what it should reproduce. If I take a rotating uncharged black hole magnetic field, so the magnetic field generates eddy currents in the black hole, the eddy currents dissipate heat through Ohm's law and slow the black hole's rotation down, and so you get out the fact that the rotating black hole in the magnetic field slows down, that the overall energy stays fixed, but there's a decrease in angular momentum. If I take a black hole, put it in the tidal field with another larger gravitational body, that perturbs the surface of the black hole. In accordance with the Navier-Stokes equation, that causes viscous dissipation. If the black hole's rotating, that causes viscous torque, and the black hole slows down. So the surface of the black hole really is just acting like an ordinary physical body with thermodynamic properties, obeying transport equations with calculable values of things like its resistivity and its viscosity. Okay, so all of that's quite striking, but the whole story I think breaks down rather sharply as soon as we think about thermal contact. So so far what we've got, I think, is a really good reproduction of everything thermodynamics tells us, including local thermodynamics, about systems in isolation. That's enough to establish that there's a really good formal analogy between black holes and other thermodynamic systems. What's relevant to get us beyond it merely being an analogy is to ask, well, what about when we put a black hole in thermal contact with another thermal system? So you might ask, what about if we try to put a black hole in thermal contact with another black hole? Even more importantly, what about if we try to put a black hole in thermal contact with an ordinary thermal body that we definitely agree is thermal, like a star or a box of hot gas or something like that? And this is where it breaks completely. So firstly, I mean, given multiple black holes, separately under the Hawking's result, each has an undecreasing area. Hawking's result holds for each connected component of the event horizon. So there can't be any process whereby I decrease the entropy of one black hole, increase the entropy of the other, while keeping the total entropy fixed. Each individual system has an undecreasing entropy. And that means there can't be any concept of heat transfer from one black hole to another black hole within classical GR. And if I imagine putting a black hole in a radiation bath, for instance, to try to get some heat transfer between the black hole and the radiation bath, of course the radiation is just going to get eaten by the black hole. Nothing can get back across the event horizon. So however cold the radiation bath is, the black hole is just going to eat it all and remove the radiation down to absolute zero. So no temperature can be assigned to a black hole other than zero. And there's no way to realize a Carnot cycle, there's no way to make sense of the Clausius or Kelvin statements of the second law while treating black holes as thermodynamic systems. So I think the right conclusion would be to say until we start thinking about quantum field theoretic effects, then black holes have a really strikingly close formal analogy to ordinary thermodynamic systems, but can't be thought of as ordinary thermodynamic systems. Of course, that seems a very unsatisfactory halfway house. And it was thinking about these situations that led Hawking, following sort of precursor work by people like Zeldovich, to the discovery that black holes seem to emit thermal radiation. And the last part of my talk really is to make the case that that completely finishes the story and gives us an understanding of black holes as fully thermodynamic. And I want to talk a little bit about the details of what Hawking radiation looks like, just to sort of show a bit of how that goes. So it's traditional in thinking about Hawking radiation to pretend it's scalar. Hawking radiation that is dominated actually by photons. We don't seem to have a massless scalar particle in our universe, but generally speaking, the physics of photons for a lot of these processes looks a lot like the physics of a massless scalar particle. So I'm going to think about scalar black hole radiation just to make things slightly simpler. So if I want to understand what Hawking radiation looks like, the first question is just to ask, okay, what are the free field modes or the classical scalar field in the vicinity of the black hole? And this is just elementary mathematics. Here's the general form for a mode of the radiation in the vicinity of a black hole. So it's characterized by the energy omega and the total angular momentum L and the z component of angular momentum m. So I have an expression that has this form. There's a 1 over r factor to make life simpler. There's a spherical harmonic characterized by the angular momenta. There's a frequency term, and then there's some wave function parameterized by the overall angular momentum and by the energy, and all of the detailed physics lives in that. But that expression is totally general for any spherically symmetric space-time. The details of the black hole space-time all exist inside the function psi there. And to describe that physics, it's helpful to change coordinates. So, if we're looking for the physics outside the event horizon, the radial coordinate that goes from -infinity at spatial infinity to 2m at the event horizon, that's an open interval in both directions. We're interested in parameterizing the physics everywhere outside the horizon. So it's helpful to change coordinates to move the event horizon out to -infinity. And if you remember the stretched horizon framework, we actually want to change what that's going to give us. The stretched horizon is going to be sort of a minus way over there somewhere, but some finite distance, and the true event horizon is generally infinity. And the tortoise coordinate r lowest star is a good way of doing that. That has roughly those properties. Far from the black hole, it just looks like the ordinary radial coordinate. Near the black hole, it stretches that space to take the event horizon all the way to -infinity. This is just a coordinate change. With respect to those coordinates, you find that this is the expression, the equation that governs that function psi. R is implicitly given here as a function of R star, and you can see this is ordinary one-dimensional Schrödinger quantum mechanics. So this physics is just the physics of a single particle with a potential barrier. This function v, that's just the one place I'll draw a diagram, so I'll do it big and bold. This function v looks like that. It's just a hump. The hump is higher the more angular momentum there is, and it has the effect of making this into a scattering problem. I can think about modes that are coming in from -infinity, which is to say from the event horizon, which is scattering off this potential barrier, and I can think of modes coming in from +infinity that are again scattering off the potential barrier, and in both cases there could be some tunneling through the barrier. So let's distinguish what get called the up modes, which are the modes that are coming in from -infinity torus coordinate. Mostly they scatter back off the potential barrier back into the black hole. A little bit they go through. Yeah.
Where is the potential barrier again?
Do you mean
I mean,
where in space, or what's it coming from?
No, I don't care where it's coming from, but you said there are modes that come from -infinity
Yeah.
and scatter off of this, and the same for the other
Yeah.
infinity. But if there are modes coming from, let's say, from the event horizon,
Yeah.
they can't be coming from inside the event horizon.
No.
So this is just a general potential barrier, and you're just studying the effect of how the scattering is happening?
Yeah, I mean, this is all formal and mathematical for the moment. All I'm doing is saying what are we going to say about solutions to the Klein-Gordon equation on this spherical symmetric space-time. And the solutions are going to include solutions that are coming in from -infinity, as well as solutions that are coming from +infinity.
Sure, but you haven't gone to a field picture yet. That was still your quantum mechanics. You haven't gone to the Klein-Gordon picture.
Yeah, I have actually. If you go back, that's possibly not obvious because we get out in relativistic quantum mechanics. So to start with the Klein-Gordon, massless Klein-Gordon equation on a black hole space-time, work out its modes. So a general mode of that has this form. Ask yourself, change coordinates to a torus coordinate. Ask yourself what equation the radial function satisfies. That's the equation it satisfies. When I say that's non-relativistic quantum mechanics, I just mean purely formally it's non-relativistic quantum mechanics. Purely formally, this is the one-dimensional time-independent Schrödinger equation for a potential barrier. The physics here is entirely classical. It's classical wave equations.
Yeah, sure.
Is there supposed to be a star in the R?
There isn't actually. R here is given implicitly as a function of R star. So invert that equation to get R as a function of R star. It doesn't have a closed form inversion in terms of elementary functions.
Okay, but I mean, I meant actually in the one of the second from bottom.
Yeah, in both cases, when I've written R, I mean to write R.
Okay.
So this expression would have a very ugly form in terms of R star. So R here is implicitly a function of R star. If you imagine inverting that equation, you can't invert it in elementary functions. I mean, you can invert it, but really only by defining a function, which is the function that inverts it. Okay, so going back to the description. So given this description, I can think about all of the possible modes come in two categories. There are up modes that are coming in from -infinity, so from the event horizon. Mostly they scatter back off the potential barrier back into the black hole. They have some small amplitude tunnel through the potential barrier and reach spatial infinity. And then there are in modes that come in from spatial infinity. They mostly scatter off the black hole. They have some small amplitude to get in. And just so you want a physical understanding of this, think about, just in a non-relativistic context, think that to throw something directly into the sun is quite difficult. Normally something will whip around the sun and come back out again. So generally speaking, to throw something into a very small compact object, you require a very low angular momentum. And that turns out that's true for a wave description as well. So light falling, contra the sort of sci-fi images of black holes as things that gobble up everything, then if I try to throw light into a black hole, mostly it scatters off again. All right, so this so far is just maths. The Hawking result is now this in this description. that if I think about my quantum field theory, so each mode described can be occupied by any number of particles, then the up modes are occupied in a thermal state. The thermal state has temperature kappa over 2 pi, where kappa is the surface gravity. And the in modes are given by whatever the ambient physics is. So in our universe, the in modes are at 3 Kelvin, for instance, yeah.
Why don't the up modes, I mean, given that the in modes scatter off the black hole, why don't the up modes like bounce back and forth between the black hole and the potential barrier?
Oh, well, they do. Well, they don't really bounce back and forth. They're coming in from minus infinity. They mostly bounce back off the potential barrier and they fall back in again.
So why do they fall in if the up ones don't fall in?
Hang on,
the in ones don't fall in.
Well, it's really just scattering theory. The potential barrier is confining things close to the black hole. So, sorry, perhaps I'm
So I get why they bounce off the potential barrier, but now I've got two kinds of waves hitting the black hole.
Yeah.
Why don't they all just sort of bounce?
The up modes are mostly bouncing back towards the event horizon, and the in modes are mostly bouncing back towards spatial infinity.
Oh, when you say so the in modes, sorry, you say scatter off the black hole. I thought you meant the membrane, the event horizon.
No, they mostly scatter off the potential barrier.
Okay,
gotcha.
Yeah, okay.
They're in the event horizon. All right, so what's going on here is that most of the Hawking radiation is actually confined to the near vicinity of the black hole. Only a small part of it leaks out. And so what you actually have is the black hole is surrounded by a thermal atmosphere, and that atmosphere gradually leaks away. And that thermal atmosphere is a thermal system in the fullest and most straightforward sense at a temperature proportional to the surface area. Okay, before saying why that matters, let me just say a bit about our degree of the extent to which we are confident about the Hawking effect. Yeah, but before that, let me take the next question.
So until bullet number 2, everything you've been saying is classical wave theory, right?
That's right.
Just wanted to make sure.
Absolutely, yeah.
Good.
So, and up till this point, everything is something that I've more or less derived for you, and you can reproduce my calculation on the previous page in a few lines. At this point, I'm then just saying, and then we derive the Hawking effect, and this is what the Hawking effect says. I'm not going to derive the Hawking effect. I am going to say a little bit about ways of deriving it. So why should we feel confident the Hawking effect happens? So one reason I think is just the range of different routes by which it's derivable. So those include you can do a matching of modes between the free field modes that describe just the exterior physics and the free field modes that describe stuff coming in from the information of the black hole process. That's basically what Hawking did. It's what you find in Wold's QFT textbook. Anyone familiar with that one? You can take the heuristic idea that Hawking radiation involves some kind of quantum tunneling over the event horizon, and you can make that precise. You can say that I want the quantum state of the black hole exterior to solve the semi-classical field equations. So I can look at how space-time is, the stress energy is polarized by the effects, and I want that to satisfy the equations. And again, that forces the modes to be thermally occupied to avoid pathological violation of the Einstein equations. I can use path integral methods on the Euclidean continuation of the space-time. The Hartland, Hawking, Israel did. That tends to be the sort of quickest and fastest, quick and dirty way of getting out the black hole temperature. I can observe that I would get an anomalous violation of the diffeomorphism symmetry of the quantum field theory across the event horizon unless I have energy flow, and indeed unless I have energy flow of exactly the Hawking number. Those are the only routes I know. They have different strengths and weaknesses. They work on different regimes and on different assumptions. What's important is these are things of a completely different calculational form in each case, and yet they all lead to the same quantitative result.
So do you mean that in a technical sense of anomaly?
I do, yeah. Don't ask me the details, I don't know them very well. But yeah, exactly. So the diffeomorphism symmetry is a local symmetry. It should not be anomalous. Local symmetries are not supposed to be anomalously broken because they're just supposed to be descriptions. So it had better not be. And to fix it, you require energy flow. Okay. You can also give a fairly good physical argument for the Hawking radiation via the Unruh effect. So if you think about this, we know from the Unruh effect that, which again you can derive in sort of 3 different ways, and which comes out of fairly standard quantum mechanics, that if you're accelerating in flat space-time, then you see yourself as being in a thermal bath of radiation and temperature given by the acceleration. If you're hovering very, very close to the event horizon of the black hole, much closer than the curvature scale of the black hole, that situation looks to you locally really, really like just accelerating flat space-time, because the curvature scale is very large compared to the distance between you and the event horizon. So what that ought to look like, according to the Unruh effect, is something pretty much like a thermal bath of radiation. The black hole fills virtually the whole sky from the point of view of an observer who's hovering just above the event horizon. Because almost all, for light to get away, it's got to leave that observer's position almost vertically away. Everything else falls back in. So from their point of view, the event horizon covers almost the whole sky. So almost all of that thermal radiation from their point of view is being reabsorbed by the event horizon. It doesn't cover quite the whole sky. A little bit can escape out to infinity, and in doing so, it gets heavily redshifted. And if you work out that redshift, you get out exactly the Hawking formula. And it's also the case that the analog models of this are now experimentally tested.
But isn't that the whole point of analog models, like having analog models, is that you can't really, the whole derivation of Hawking radiation is based on the fact that this redshift happens, but when that high redshift happens, you require energies at which your theories, your normal CSQFTs is no longer valid. So isn't the derivation kind of, I mean, we don't even know if this result is acceptable yet, right?
Do you want to wait till the end?
Yeah, I was going to say, I
we'll
think
do
that's
like
not a
a
question of
Q&A
clarification.
session at the end, and I'll put you first
Yeah.
to the people.
I think I'll have to take questions of clarification at this point. That doesn't strike me as a question of clarification. All right, so assuming Hawking radiation is there, what do we get from that? Well, boringly, it fixes the proportionality constant of entropy. But much, much more interestingly, it gives us that mechanism for energy transfer between black holes and other systems. The easiest way to do it is just to say, well, that this black hole's radiating, this black hole's radiating, so they just absorb some of each other's radiation, or this black hole is radiating, this metal box can absorb some of it. If you want to lower in boxes of radiation, let them fill with Hawking radiation, pull it back out again. Again, notice that what you're doing is you're lowering into the thermal atmosphere, which is pretty much in equilibrium, let it fill with equilibrium radiation, pull it out again. You can set up energy flow between black holes and other thermal systems pretty much the same way we were setting it up for the Sorkin et al. Model. Again, because these are gravitating systems, just physically putting two black holes close to each other is not a good strategy, but that's for reasons that we're already familiar with in other bits of gravitational thermodynamics. And indeed, Unruh and Wallace show that you can run a Carnot cycle perfectly effectively, you can reproduce Clausius and Kelvin-Burgess laws. Effectively, you can just mine bits of the black hole atmosphere by lowering boxes and pulling radiation out again. And just a way of seeing this really is that the black hole, you're not really ever interacting directly with the black hole, but the black hole's atmosphere is just like any other ordinary thermal atmosphere around a dense body. In fact, a way of describing all these results is that if you were to replace the membrane of a black hole, which is fictional, with a genuinely physically real membrane of some implausible substance that had the sufficient stress and strain to stay of just the right size there, you couldn't tell the difference from any process outside the black hole. So I said I'd talk about black hole statistical mechanics if I had time, but I think I haven't, so I'll skip straight across that. Conclusions from that. Classical black hole thermodynamics, without thinking about Hawking effect, reproduces ordinary thermodynamics just fine for single systems. It totally fails to reproduce thermal contact. But the Hawking effect completely fills that gap. And so the claim is going to be the stretched horizon of a stationary black hole behaves exactly like a self-gravitating thermodynamic system. And then, of course, if that's the case, it becomes enormously tempting to ask, is there a statistical mechanical underpinning of that? It seems prima facie implausible that every thermodynamic system in the universe, bar one, has its thermodynamic behavior as a consequence of applying statistical mechanics to an underlying quantum dynamics. And so then the question of how much can you reproduce that in quantum gravity becomes an urgent question, but that's another story. I'll stop there.
Thank you. Okay, I'm just going to move the computer so I can, if necessary, in case I need to put the control on. So I'm going to make these guys a bit bigger. These guys a little smaller. But it is our custom to have people from Geneva ask questions first. And surely Chris has something to say. Can I, so this is the mic over here, so some of you are quite a ways back. If you have questions, speak in this direction in a loud voice. That would be great. I'm going to let them.
Do you hear me?
Yeah.
Okay. So, I have a lot of questions about the smaller things, but we're a little bit short on time. Let me focus on the really big question relating to what you said at the end, or I think you should have said at the end, at least it's on your slides, and that concerns quantum gravity. And what we learn from all of this going forward to formulating a quantum theory of gravity. Maybe one way to ask the question is this. Suppose we formulate a quantum theory of gravity based on theoretical considerations, which are extremely convincing, very suggestive, physics that sounds basically right, but there's no empirical confirmation for any of that theory. Just as there's no empirical confirmation of Hawking radiation, say, or any of the thermodynamic phenomena here in black hole physics. Now, however, it turns out that this new theory of quantum gravity contradicts some statements of black hole thermodynamics. Suppose it doesn't reproduce the same formula for the entropy. Maybe it may predict no radiation whatsoever, or radiation that's inconsistent with Hawking radiation, or something like that. What would we do then in that situation?
Well, look, I think in a certain sense it looks super exciting. We're assuming antecedently we've got really good reason to like this theory. But what you're going to want to do is say, okay, so how does this thing get the low energy regimes right? I mean, one of the conditions on a quantum theory of gravity is it needs to get low energy physics right. These are all results of low energy physics in an untested regime. So this new theory is somehow managing to get all of the predictions of low energy physics right in the tested regimes, and yet to deviate sharply from that in these untested regimes. So I think really you want to look really closely at how that's happening. Yeah, how has this theory managed to work this way while contradicting, say, the physical argument gave for the Unruh effect, while contradicting Euclidean calculations of entropy effects? How's all this happening? Normally, what we try to do in a low energy theory of quantum gravity is we want to say either better get out the low energy regime, so we better get out something like quantum field theory on a curved background. We better get out something like GR and effective field theory. If this thing is not doing that, and yet is somehow still getting us out at the enormous accuracies we need, low energy physics and quantum field theory on flat space-time, it must have some super remarkable properties. And I think you want to look at that theory and look at that super remarkable properties. If the theory's got built inside it a really good theoretical explanation of why all this is happening, then of course that's fine. But this is the context of discovery. Prior to having those things, we can reasonably think that looking for such a thing is going to attract. I mean, take a case study. Take something like loop quantum gravity. So in loop quantum gravity, if we had developed loop quantum gravity to the stage at which we had a really thorough and good recovery of the classical and semi-classical regime that thoroughly handled classical GR, reproduced gravity waves, reproduced the standard model in CERN, etc., etc., etc. If we had that, then we wouldn't particularly. Then we might feel relatively sanguine about the theories not reproducing black hole thermodynamics. I mean, if it did, sorry, I'm counterfactually, if it didn't reproduce some detail of black hole thermodynamics. Given that we're not in a position to get out that semi-classical regime in loop quantum gravity last time I looked, then we might have substantially more reasons to be uncomfortable if loop quantum gravity failed to reproduce some aspect of the black hole thermodynamic regime. That's the sort of structure I think you have to do. But again, I think nearly all of this stuff is context discovery stuff.
Maybe
I'm going to put this up here so you can look at them here, and then you're kind of looking at the camera.
To state it slightly more positively, if I may, that means then that there's some sort of a heuristic constraint or something like that on a theory of probability to be a theory of micro degrees of freedom that allows us to do some sort of statistical mechanical counting, which gives us reproduces the correct entropy, for instance.
Well, look at it this way. If the theory doesn't do that, it has a lot of questions to answer. If it can give good answers to those questions, that's cool. So, if the theory reproduces, but I mean, let's put it this way: if our theory of quantum gravity actually gets us back out the fact that a black hole can be treated as a quantum system where log dimension of its Hilbert space equals the semi-classical Bekenstein-Hawking entropy, at that point black hole thermodynamics is totally unmysterious. We would just expect black hole thermodynamics given all of that. If this theory does something different, it had better tell us why all that stuff works. Maybe it's got a really good answer to give us, but it owes us an answer. Hi.
Thanks for the talk. I have a question, or a set of questions, but one of them is, to what extent does the membrane or the stretch horizon rely on the notion of event horizon? And so it inherits some of the features of the global event horizon?
Sure. So I think, insofar as you're worried about how to define this thing globally in the strongly non-stationary regime, I think it inherits all the problems. I think that's an important question to think about. I don't think it's directly salient to black hole thermodynamics, because thermodynamics is about equilibrium systems, and in equilibrium systems those problems basically go away. But yeah, and if you wanted to ask, okay, how do I think about black holes as quantum systems in the strongly non-equilibrium regime, I think there are deep questions there that are not resolved or sorted out by the membrane paradigm.
In flat regions, is that correct?
I missed the first half of that.
But, we could have the membranes, the stretch horizon developing in flat regions as well.
Well, exactly, that's right. So in the strong, well, I mean, the fact it's flat looks fine anyway. I mean, if I have ordinary black, if I form a black hole by a infalling light shell or something, then that's definitely going to happen. But that doesn't seem problematic. But you might have them turning up in weird places, and I think that's right. I don't think much is known about whether I can think about whether there's a good theory of strongly non-equilibrated black holes. It might be that. And I think it might be the right thing to say is that certain regions of space-time could be thought about as quantum mechanical systems, and the equilibrium states of those regions can be thought about as stationary black holes, but there isn't some way of saying that the strongly non-equilibrium regions are characterizable as non-equilibrium black holes, or even are characterizable in classical space-time language at all. I think those are wide-open questions.
Hi David, thanks for the talk. So I was wondering about what you make so the possible generalization of dynamics to horizon dynamics, and whether you think you could also make a case for the horizon dynamics should count as some kind of dynamics problem. So what I have in mind, for instance, is say a window horizon or a window observer, and you might attribute some entropy to it as well, and you might attribute some temperature to it, thanks to Umbu effect. Have you any thoughts on this? Or?
Yeah, I mean, only to the same. My thoughts broadly summarise as, that's really mysterious, isn't it? I mean, there's clearly some sense in which the Rindler horizon, from the point of view of the accelerating observer, is functioning as a quantum system and can be probed in that way, but the degree to which that's fully robust in the way the black hole one is, I'm not sure about.
Are you guys done for a bit? Yeah. Let's take some questions from here then. Do you wish to ask your question?
Yeah, the whole premise.
It's nice and loud so they can hear as well.
The whole premise of the conclusion that you can treat this as a thermodynamical system when it is not just individual systems is that you you can talk about two black holes talking with radiation.
Yeah.
But that whole result is a little bit shaky, right?
Mm-hmm.
So we don't know. I mean, even in analog models, I don't think it's been conclusively established that Hawking radiation is a thing. Given that, how I mean, I agree that it's very tempting because these thermodynamic laws are very similar.
Mm-hmm.
But I'm still not convinced about the Hawking radiation.
Oh, well, I don't think you could. I mean, it depends what you mean by convinced. Should you bet your life on it? I wouldn't. It's not actually, it hasn't actually been observed. At some level, one should be empiricist. But, at what level do we think a theoretical prediction of our theory that's none observed is a prediction to take very seriously? I think we're very much in that space.
No, I don't mean about the observation at all. I mean the result in itself, the derivation, the theory of it.
Okay.
That itself is shaky, because that is trying to talk about like when we do the mode matching, for example. This is all happening in curved space QFT, but if you do have modes propagating from such close distances to the event horizon, you're bound to have energy scales at which your theory that you're using to compute the result is not valid anymore.
So the best answer I know to that answer is Polchinski's answer. Let me just sketch that. You may well know it, but just for others. So again, I'll try to draw really big for Geneva. So here's the black hole space-time. So the Hawking calculation is generally done on this kind of foliation, and it's certainly true that in doing that, I'm committing myself to details of how the quantum field theory extends on arbitrarily high energies as I get closer and closer to the event horizon. And because the modes, as they redshift away, exponentially decrease in energy, then it looks on the surface of it as the theory is really digging into those features of it. Okay, so Polchinski points out that I could perfectly well do my quantum field theory description, but here's my singularity. I could perfectly well do my quantum field theory description if I wanted to on slices like this. And on slices like that, everything's well behaved. There are no high energy, there are no trans-Planckian high energy goings on. So that's a situation in which the predictions of low energy quantum field theory are reliable and robust. Since the predictions of low energy quantum field theory are reliable and robust in that situation, I can, as usual in QFT, I can do my high energy cutoff in any way that I find convenient, and in particular I can do it in the way that Hawking does by just naively extrapolating the theory to infinity, and I can be confident I get the same answer out. That's the best response I know in the theoretical side for trans-Planckian concern. I mean, if they want a more sort of philosophical response, I think my response would go something like this, that if there isn't a response of that kind, if it doesn't work in some respect, then so many other things seem to break somewhere. I mean, so for instance, if the Hawking modes aren't occupied, then the space-time around a black hole is extraordinarily negatively polarized and radically violates the Einstein equations. So the Schwarzschild solution doesn't remotely solve the equations in curved space-time QFT with no Hawking radiation. So we shouldn't kid ourselves in thinking that there's a legitimate theoretical space that's occupied by saying things are as we thought they were, but there's no Hawking radiation because it's something we don't understand at the ultra-Planckian regime. If there's no Hawking radiation, our whole picture of curved space-time QFT is catastrophically broken in ways we don't remotely know how to think about. So that's the sort of more philosophical side of it. But I think the Polchinski nice slice argument, at least I find pretty persuasive.
Can I just?
Since
I can, I'm going to just give myself a finger on that. I mean, this is something people who do the analog experiments say as well, is that the analogs also have a trans-Planckian regime, and the fact that they see the Hawking radiation then gives you, I mean, that's the power of the analogs.
Yeah,
that if it's, if you don't have to worry about, if it's insensitive to the Planckian regime, in the analogues, then that's reasons to think that it is in GR as well.
No, there is the Transplanckian problem in the analogues as well, but there's a nice way to get around that, because I mean the whole formalism of the analog models is still based on the metric of it, right? So though you know the microphysics of these things, you can still run into such a problem, but there's a nice way of getting around it in that you can actually compute the density correlations between your particles, which are inside and outside the horizon, and those are not affected by these things. So studying their entanglement or correlation functions kind of gives you an idea about whether there is Hawking radiation or not. So even though there's a similar problem even in analog models, there's a very nice way of dealing with them here. And yeah, I don't know, the last time I looked at papers about these things, no experiment or even theory for that matter has conclusively established anything of the sort. Not deep. I don't know of a model that does this very well.
I mean, I think there's a more. I didn't really stress the analog models partly because I'm not super au fait on the empirical data, and you were skeptical of some of it, and I didn't have a good response to that. But if I were going to run an analog line to answer this question, the line would be something like this: that the calculations that are done in the hypothesis is that the fact that the calculations have trade on Transplanckian details is a harmless artifact of the goings on and doesn't undermine the basic calculations. So the fact that I do the basic calculations in the analog models and the analog models have a Transplanckian problem, and yet in the analog models the phenomenology works outright, is evidence that indeed it's harmless. That's the way I cash it out. But I think you can do it more directly. I also don't have much of a sense of the if I'm working out a Transplanckian problem. I mean, if I'm doing if I just think about, say, just Euclidean model justification of the Hawking effects, I'm just doing quantum stat mech of the field in equilibrium. I mean, the physics of the radiation of those radiation modes far from the black hole, or some supra-Planckian distance of the black hole, at full equilibrium had better be ordinarily thermally occupied in the normal way, and there's no deep physics going on there. So even though we don't know how to extend those modes arbitrarily close to the event horizon, then we don't need to extend them arbitrarily close to the event horizon to know that a black hole at thermal equilibrium with distant radiation is going to have a local temperature given by the Hawking results at, let's say, 1 1/4 short radiuses from the event horizon. So it's not clear to me. It's not very clear to me how much the Transplanckian objections really trade on the details of the original Hawking Zeldovich type calculations, and how much they really threaten any of the quite large number of other ways people have of deriving Hawking radiation. I think that you look skeptical, but that case would have to be made.
Very good. Okay, yes, please.
Yeah. So I guess the thing that's kind of strange about black holes has to do with the event horizon. And if you have a system, a classical system that has information in it, like a gas or a deck of cards even, or anything, and you drop in the black hole, the information seems to be gone from our universe, so the entropy has decreased. Now, I guess at some point they decided that the area of the black hole increases because that's proportional to the mass squared or something. So that presumably is a way of compensating for that. But even with Hawking radiation or whatever, is this problem still a problem?
So I've intentionally avoided that line of reasoning for black hole entropy, which was very influential in Bekenstein's work. And the reason I've avoided it is because it's controversial in ways that trade on philosophical puzzles and statistical mechanics I don't want to get dragged into. But just to engage its own terms, so what we would like to establish is a generalized version of the second law of thermodynamics that says within semi-classical physics, quantum field theory on curved space-time, that says something like the total thermodynamic entropy of the black hole exterior plus 1/4 the area is a non-decreasing quantity. Quantum field theory looks like it probably solves that problem. it would solve that problem if in quantum field theory there were hard minima. There was some kind of hard limit of how much energy you can get into a given spatial region and how many degrees of freedom that region have. So that Bekenstein bound has been proven in relatively recently to a fairly serious level of mathematical rigor, and that generalized second law has been proven again in the last 5 years to what seems to me, as a non-expert in the details, a pretty solid level of rigor. So I think the case there has become a lot more solid, but it's taken some while.
Sebastian.
Thanks for the talk.
Yeah.
I have a simple question regarding the classical black hole thermodynamics when you derive the equation, suggesting that it has the same functional form.
Oh yeah.
Yeah. So regarding that point, I was wondering if you. So you said it has the same functional form, and also the physical interpretation of some of the variables is similar, but of course, like in one case you have angular momentum. In the case of the black hole, you have angular momentum and current. In the case of thermodynamics, or at least in simple thermodynamics, you have energy, and you have work, or you have something like generalized work, or something like that, and you have entropy. So the fact that they have the same functional form, of course, shouldn't be enough to say that, because many equations will have the same functional form, and the interpretation is not clear to me that you can read like, oh yeah, this is kind of thermodynamics because the variables are not exactly.
So I think in most cases they are. So suppose I have a system that's characterized by an ordinary thermodynamic system, not a black hole, that is characterized only by its energy, its charge, and its angular momentum. In other words, those are the conserved quantities that fits its equilibrium states. So suppose I've got a system of that kind. The general functional form of its first law will be du equals TdS minus omega dj, where omega is the angular velocity, plus omega dj, so I'm not sure the sign, so let's assume minus omega dj, where omega is the angular velocity, minus phi dq, where phi is its electric potential. That's ordinary thermodynamics. So now if you do a match case, well, in relativity, mass and energy are equivalent, so the U matches up, the angular momentum matches up, the variable conjugate to the angular momentum matches up, the charge matches up, the variable conjugate to the charge matches up. So the only thing that isn't the same, and might only just be formally analogous, is the TdS component. That's the case to be made.
Randall.
You mentioned this second part of the talk about radiation kind of completing the picture of equilibrium.
Yeah.
That kind of brings to my mind the concept of extremal black holes. In theory of the supersymmetry, this do not radiate. They're stable. In fact, they're dual to stable particles in theories and things like that. So there's nothing wrong with those black holes, really.
Yeah, they just had I mean, those are genuinely at absolute zero.
Those are what?
Those are genuinely at absolute zero. The temperature we want to assign to those things really is zero.
Oh, I see. So there's no reason for any equilibrium between them. That's what you're saying.
Yeah, and I think the right way to think about extremal black holes is, and this is not meant to be a particular original observation, but extremal black holes are ground states. How do I get a system? I mean, how do I get a system to extremality? It's increasingly difficult as it cools, as it gets closer and closer to extremality. Its temperature goes down and down, so the amount of radiation it gives out gets lower and lower.
I thought there was a way to calculate the entropy of
Oh, absolutely,
states.
No, absolutely. Just
Even though they have no temperature.
Oh, well, they don't have no temperature, they have temperature zero. Zero is a perfectly well-behaved value of the temperature. I mean, one of the reasons why extremal black holes have been an important calculational source in black hole statistical mechanics, at least in the string theory route to it, I think is precisely because they're like ground states, and it's usually way easier to do the statistical mechanics of the ground state of a system than it is to do the statistical mechanics of the cyclic states.
Just building on that, there's another way of thinking of these black holes, these extremal black holes, as just particles, essentially. So you can ask the question about what type of statistics a gas of these black holes has. Is there any any answer to that from any of these points of view?
Well, the thing to be cautious with there is, I mean, you can think of them as particles, but the disanalogy there is they're particles with an extremely high number of degrees of freedom. So an extremal black, typically a particle has no or only a very small number of internal degrees of freedom, but an extremal black hole has a macroscopically large entropy, a macroscopically large, on a statistical mechanical model, has macroscopically many degrees of freedom of its own. Now, you could, I guess if you would say, well, nonetheless, I've never mind that, I want to suppose those degrees of freedom are not excited at all, and I'll just consider a bath of them. I mean, I don't know anything about that, but I wouldn't have thought anything very deeply interesting is going to happen. I mean, in the same sense, I can imagine it just in classical astrophysics, I can imagine, sometimes in celestial mechanics models of galaxy dynamics, one actually thinks about this. I can have a gas of massive particles, and I can do it in statistical mechanics. And at that level of analysis, it doesn't matter very much if they're black holes or just stars or something. So I think we'll write that down. I'm not sure how closely we'll plug into these kind of considerations. We kind of like in the sense that there's a statistic. If I imagine a gas of stars, then there's the entropy that each individual star has, and then there's the entropy.
There's a mechanism for them to interact also, right?
Yeah, there is, and in principle that's going to happen for black holes as well, because if I have two black holes that pass very close to one another, they'll be perturbed away from stationarity, and the damping of that perturbation will generate heat, and if they're extremal, it will divert them away from extremality. But again, just as in the star case, unless the gas is enormously dense, then that's going to be a very minor factor.
So I have two shot, but maybe let me. Since you guys will be ask like after over here, yeah. One last question.
This probably isn't really covered directly in your talk, but when you talk about black hole statistical mechanics approach to black holes, the string theory approach uses deep breaks. No, I'm not a string theorist, but I looked at that significantly. I'm wondering, do you have any comments about the feasibility of this approach? Because we know that to reproduce some of the results, the Wittgenstein entropy requires you to have things like you have to go to a non-coupling regime, or you need to use things like invoke supersymmetry without breaking it. And things like D5 branes as well require 9-dimensional spaces, which brings us further and further away from what I think we are familiar with in our Schwarzschild solutions for our universe. So do you think this approach is probably more of a curiosity, mathematically speaking, in reproducing the results, or it could actually be promising? And do you have any thoughts on that?
Yeah, I know. I think the results are pretty important, actually. Although don't ask me to tell you the details of how they work. So it's certainly true that the situations we're describing are somewhat exotic. What are they? Well, firstly, they're extremal. That's not, I think, surprising. Again, it goes back to the point that extremal systems are easy to treat. As I understand it, and I'm no expert on this, then the results on extremal black hole entropy, at least the first order results, turn out to be not really drawing on deep features of, or specific features of string theory, but just on those features that come out of ADS-CFT correspondence. So, at least at that sort of first order of analysis, you can more just think of these as ADS-CFT results rather than specifically string theoretic results. And in that framework, you can still raise concerns about physicality. We have there are different grains of ADS-CFT. The concrete precise models of ADS-CFT we have are all supersymmetric string theoretic models. Those don't seem to describe our own universe, or just our own neck of the woods. But we have quite good heuristic, qualitative, in some places quantitative evidence that ADS-CFT holds significantly more generally than that. And we have, this is very much cutting-edge things, and I don't think it's quite ripe for a conceptual assessment yet, but the Kerr CFT correspondence results of the last 5 or 10 years seem to put us really very close to using those mechanics to reproduce the entropy of non-extremal Kerr black holes in full space-time dimensions. So I think that's gone a long way. The other side of it, I think, is the question with string theory. Here's the question you ask for string theory: is string theory a consistent quantum theory of gravity, or is it a trick of the light? And one of the sorts of concerns people have had about string theory is that while we can only characterize the perturbative regime adequately, and the whole thing is just built on sand. And I think the success of the extreme black hole calculations is really powerful evidence that there is a consistent theory there, whether or not it's the correct theory of quantum gravity. And what, I mean, just to catch that a little bit more, so if in black hole, if I use entirely low energy results in quantum field theory, but still using statistical mechanics to work out the entropy of black holes, I can do a zero order approximation and a first order correction and get a quite detailed, complicated expression for the black hole entropy that has logarithmic corrections and renormalized terms and what have you. And if I then calculate that same quantity via string theoretic dualities, I reproduce exactly that expression, all complexities and all numerical coefficients and all. And it's again very hard to see how that could happen. It's not, of course it's logically possible as a coincidence, but it's hard to really see how it could have happened unless there really was a well-defined theory that indeed had a statistical mechanics that was built through there. So that doesn't tell you that string theory is true. It doesn't even tell you that there's a consistent regime in string theory that describes our own universe, which has 4 spatial dimensions and 4 large spatial dimensions and apparently no unbroken supersymmetry. But it's, you know, it's significant. It's a satisfactory response at least to one class of criticisms of string theory, i.e. that there's no there, there's no well-defined code.
Okay, well, it's getting very late in Geneva, and I guess it's getting lunchtime here. So let's say goodbye and thank you very much. Great talk. And there you go, you can hear them clap too.
Thank you very much. Very interesting talk. Thank you.
Thanks for coming.
Should I click finish on this? Is this the button to
The
finish?
next talk I have, by the way, I have is going to be here on, I think, November 15th. Yes, stop that. Laurent Friedel is coming from Perimeter Institute.